Yeah, let's jump right in. So, yeah, for this talk, I'm gonna be going over basically a bunch of practical tips for implementing game agents. So, yeah, I know that you've all been starting to work on your projects and you've learned a lot of different techniques over the semester. And so, figured it'd be great to have a chat about how do you actually do this practically. It's one thing to think about the techniques and how to actually build out these bots, but getting into the actual nitty gritty of adding it to a game can be quite challenging. There's a lot of little things you're going to run into or little issues that might be challenging. So we're going to be going over how to make that task a little bit easier. So just to start off with a little bit of introduction, yeah, so my name is Aaron. I'm the founder of Regression Games. It's a company that I founded in May of 2022. So we're almost exactly 2 years old now. And we are VC backed by NEA and A16Z, which are two venture capital firms. And I'll go over a little bit about the history of the company in a moment. But right now, what we're primarily focused on is building tools for making AI agents in games, primarily around automated testing agents. So the idea being that you might have a game, you might have a QA team that's doing a bunch of play testing every day, trying to find bugs, trying to find issues. Our goal is how can we actually automate that process using AI agents across a whole bunch of different techniques, a lot of which you've probably learned during this course. So um, yeah, that's a picture of us down the corner of our team. We're a pretty small team right now. Right now, we have 4 engineers and one intern as well. And yeah, we're all remote, located across the US and Canada for the most part. And a little bit about my personal background. So before Regression Games, I worked at another AI startup called Instabase. And what Instabase does is essentially ML for document processing. You can imagine that maybe you're a big bank and you want to process loans. How do you build out the machine learning and AI capabilities for extracting information from documents like pay stubs and you know this any sort of document that might be uploaded for that sort of use case. And so I've done a lot of work in the past, especially around like 2018, 2019, with some of the early transformer models. So at that time, there is not really large language models, but what I would just call probably just language models, pretty small models that are just beginning to be like multimodal in some way, starting to look at text, but also images and things like that. And so I worked a lot there on machine learning operations side. So how do we actually train the models? How do we host them? How do we make them usable for our customers? And so did a lot of work there. And then previous to that, I also worked on AI agents for a competition called Battlecode. Some of you may be familiar with this. It's an annual competition put on by MIT every year. It's basically like an AI competition where people come in and build an AI agent for a game, and your goal is to beat other competitors. It's a lot of fun. Definitely recommend checking it out. The website is battlecode.org. Usually it's around like the end of the year, January. So hopefully if you can hone your skills, learn from this course, you can apply it to a fun competition. So definitely recommend that. But yeah, so I worked on that for quite a few years, both as a participant and then helped run that competition. And then previously before that, like about you mentioned, I worked on AI systems for mobile testing. So how can we build really simple like rule-based systems for testing that apps are accessible was mainly what I was working on. And so yeah, so most of my background, most of my career has been working on just machine learning applications, mostly around sort of like AI systems, whether it be like mostly NLP, I'd say, but also some reinforcement learning, some machine learning, just kind of everything across the board. So yeah, so I figured I'd start off this by just kind of giving a little bit of context on what we've been up to at Regression Games and sort of like the AI systems that we've been building out. So the very first thing we started as was actually not really a company for building like AI systems for game studios. We were actually more kind of taking that idea of battle code and actually bringing it to the mainstream. So trying to make a tournament platform for people to build AIs and compete against one another. And so the very first competition that we ran was called the Alpha Cup. So this is back in 2022. And the idea is that people will build AI agents in a Minecraft capture the flag challenge. The goal was, build a team of agents that can cooperate together to capture a flag, defeat the enemy team. And so that was a lot of fun to build out. It was a very interesting challenge, like trying to get Minecraft agents to work. As you probably know, it's like a pretty popular, sort of game to play test with agents and, do some research. And so there's a lot of existing literature to kind of pull from, but there was a lot of unique challenges of getting Minecraft agents to work. turns out Minecraft is very buggy, so it can be very difficult. Um, but yeah, so that was a lot of fun. We were focusing on that at the beginning of the company. But after a few months, we after doing a lot of play testing, getting feedback from players, we decided to focus a little bit more on building out this AI, taking this AI system that we built for Minecraft and then applying it to different game engines, like the Unity game engine is the one that we mostly work in. And so shortly after this, and up to, I guess, very recently, we've been mostly focusing on how to automate tests in Unity. There's a lot of use cases for agents, as you probably already know, and I'll be going over some of those as well in a slide eventually. But right now, we've been focusing mostly on automating things like smoke testing or functional tests or regression tests within Unity games. How can we build agents and systems for not only controlling a character to like move through a game and find different bugs, but then also do the reporting of those bugs, capture performance information, capture all the data you need to actually, fix those bugs that I might find. And so overall, it's been a lot of fun just like exploring the space of using all these different AI approaches and applying them to games, getting game agents to, do something useful. And there's a bunch of different things that we worked on, like different prototypes. So another cool one that I figured I'd show off initially as well is that we've been doing some experimentation, for instance, with LLM-driven agents for UI testing. And so if I click this video, basically what we did was we had a tool in Unity where you can give it a goal, like in English language. So right here we say, the goal is to reach this scene by, clicking on these different buttons. And then we actually had an LLM, observe the state of the screen and then decide what to do based on that prompt and the different states and actions that we have available. So yeah, so I want to kind of give a quick overview of, the things we've been working on. Lots of cool experiments. I think that's one thing that I love about this space is that there's just so much to try out and experiment with. But overall, so yeah, we've done things with LLM-driven UI testing agents. We've done things with computer vision, trying to just look at a screenshot and understand the entities and what's going on in a game. We've done a lot of work with writing code using LLMs for things like behavior trees or just bots in general. I'll show some of that later in these slides as well. Then we also done a little bit with things like imitation learning, reinforcement learning, more code generation, a bunch of cool stuff like that. And so, yeah, so over the past year, we've been implementing agents and agent tools for game studios. And really what I wanted to do today was kind of share some of our learnings from just us working on this almost every day, just trying to build out agents for different game studios, trying to integrate these systems into real games. There's a lot of really unique challenges that are, definitely pose like some issues when you're actually trying to onboard these agents. It's not always as simple as just connect an agent to your game and it just works. There's going to be a lot of decisions that had to be made when you're actually looking to do that integration. So I guess kind of alluded to this already, but yeah. So in this class, I know you've been learning about different approaches for implementing agents, whether it be behavior tree tools or maybe using LLMs or also doing like reinforcement learning. There is like a lot of different approaches for implementing agents, and I think that might be one of your challenges as you work on your projects is deciding what sort of approaches you want to use and what's decent for your use case or your game. And like I mentioned, what we're going to be going through in this talk is some of the actual like very specific sort of examples of like where things start to break down. One game I'm going to be looking at often in throughout this deck is the boss room game, and I'll show that in a minute as well. But essentially, it's a dungeon crawler game where you have a couple of characters you can choose from. It's a multiplayer game, and the idea is you try to progress through the dungeon and then eventually fight a boss at the end of the dungeon. And so as we started, to really dig into this game and start adding agents to it, we ran into a lot of roadblocks related to a bunch of different sort of components in that game. And so we'll be kind of going over some of those aspects and how we can actually like kind of address those and kind of think ahead and make it easy to structure our agents in these games. And then overall, the way I've structured this is I have like 5 overall principles to follow. These are kind of like high-level guidelines, and we'll dive deeper like with real-world examples from studios and games we tried out to kind of show like where these principles sort of break down if you don't follow them correctly or if you don't really think about them early enough. And then also there's a bunch of other like small tips and tricks that we learn throughout our time implementing agents. So this presentation ends with just like a few slides about those different tips and tricks. Also, one thing I will note is that because we work with Unity, some of the code samples in here will be with like Unity and C Sharp. It might also like be looking at the Unity editor and things like that. But don't worry, I know that I think in this class you guys were all focusing on Godot for the most part. Um,
We ended
or
up using Unity
oh,
after
cool,
all.
awesome. Well,
Yeah.
that makes it even easier then. Um, so yeah, so most of the slides in here will talk about Unity. Some of them also mention things like Unreal or Godot as well. But yeah, that's good to know. All right. So principle number one here, and this one's like pretty, I guess like pretty obvious, but also it's very easy to forget about this. But you really do want to think about adding agents like early on in your game development. And really the key point here is that games get complicated very quickly, and it can become very difficult to add extra features like agents on top of your game if you don't think about it ahead enough. And so, I mean, when you're building out a game, especially more larger and complicated games, you're going to have all the different, core game logic. How do characters move around? How do things get spawned? How do you move from scene to scene in your game? You might have multiplayer networking issues. So we'll dive into that a little bit deeper in these slides as well. But when you start adding multiplayer and different networking aspects to your game, there's a lot of things that start popping up that makes it difficult to add NPCs or agents. There's things like animation rigging. How do you actually make sure that your agents are playing nicely with the other systems that are controlling characters like these animations. There might be event systems, might be external APIs. There's just a bunch of different things that start to pop up as you get further and further into your game development. And so it's really important to think about like how are you going to structure these things to make sure that an agent can actually like sit nicely within the context of your game. And I'll be showing some examples in here of like games where that was not the case, where it was not thought about early on, and you'll see how it's quite challenging to add agents. Um, so yeah, in addition to just thinking about agents, really the first thing you probably want to think about is like what is the application of your agent. There's actually quite a lot of use cases that I'm sure some of you might be exploring like in your projects. So for instance, maybe you might have multiplayer bots. A lot of games have this, for instance, like either Fortnite or Apex Mobile or a lot of the multiplayer games these days have agents that are acting as humans like in a multiplayer game. These are often like really useful for people who are like just getting into a game. They want to, face bots that are like easy to beat. And so that's like a very common use case these days. Of course, NPCs, anything that's in the game that maybe it's not like a multiplayer bot, but anything you're interacting with that is a character that needs to do something a little bit complicated or has dialogue. That's obviously a very common use case. QA and game balancing. So that's a use case that I personally been focusing a lot of my time on and our company's been focusing on. Can you build agents that will actually play as a player and, find bugs in the game, either by exploring the game or following some sort of scenario that you want to test out. And then finally, this one's been interesting as well more recently, which is coaching, which is can we build agents that will help players learn how to play a game more effectively? This has been done somewhat in a simpler way in the past here. For instance, like in the Valheim game, there's like a crow that will, kind of teach you, how to play the game and give you some advice. So that's kind of more on the basic level. But even more recently, I actually had a really interesting conversation with one of the AI leads at Riot Games, and they're thinking a lot about how can they have AIs that can actually like play alongside the player and teach them how to play. Actually like reading like their inputs and saying, hey, at this point in the game, I thought you should have done this instead of this. And so there's a lot of different applications. And I guess the main point here is that you want to think pretty clearly about what your application is of the agent, like what's your use case, and you really want to think about the goals of that application as well. Just because you might have a multiplayer bot, for instance, doesn't mean you need like the most strongest NPC ever, right? You might just need like a very simple agent running. So I think it's really useful to like actually write those down at the beginning of your project properties, like, hey, this is like what I want my agent to achieve. Here's like what a successful agent looks like. Um, it's very easy to forget about that. I'll share some anecdotes from studios we talked to or worked with where often they'll think they want like the most complicated agent ever. It actually ends up being like pretty simple. So just as an example here of like I mentioned, there's this game Boss Run. This is the game that I'll be talking a lot about during this presentation. But basically, Boss Run, like I mentioned, you control a character and you have different abilities, like an attack ability, a block ability. You can choose different characters as well. And the goal is to get through the dungeon and eventually fight a boss in some boss room at the end. So I'm going to go through some examples of like where in this game like it actually got really difficult adding agents to it. So our goal was, like I mentioned, how can we add an agent for playing as a player in the game? And there's a lot of really unique challenges that came up trying to integrate it into this existing game that, didn't really think about this beforehand. So here's one example that I mentioned earlier about like animation rigging. So a lot of actions that a character might take, for instance, are not just, the game logic side effects of that action. You also need to think of things about like animations, how does it interact with other things in the scene. And so that was actually one thing that made adding agents very tricky is that, for instance, let's say I wanted to have my agent move from point A to point B. I couldn't just say, hey, use this nav mesh or use this navigation system to move it. I need to actually not only move it, but then also play the animations for that character, right? And so because of the way they had the game set up, it actually was pretty difficult and like pretty like intertwined to in terms of how they treat the animations and the actions. And so it actually made it pretty difficult to like get an agent working initially, where our very first pass of this, the agent would just like move to a new location and just like be completely still the entire time. Like it would just be in its idle animation state. And so that's why it's important to kind of think about like the sort of the how these your systems play together inside your game, and actually try to build out maybe like an interface or a way for those things to be joined together in a way that's like easy to call into later on for your agents. Another thing that made this integration really tricky was the networking aspect of this. Because we wanted the player to connect as, or we wanted the agent to connect as like a player in the game, that brought up a lot of different issues with respect to how clients would connect to the game if you're playing it like in a multiplayer fashion. And so, for instance, if you're not familiar with this code, that's fine. But basically, how this networking framework works in Unity that they're using is that you have these variables called network variables, which are synced across like the network for different clients. And so, for instance, like in this case of the character, I have this like health state that's a network variable. So then that means that every client can like see the health of that character. And so that's great for the multiplayer part. Like it means that, everything's working properly. People can see, what's going on with that one character, that one client. But the issue is that if I want to add an agent to this game that's not controlled by a client, like how do I even begin to add that to the game? Do I, need to simulate a fake client and have it connect? Do I need to rework all these network variables to also support like a single player sort of agent where it's like just within the game server itself? There's a lot of really tricky things when you start diving into multiplayer, and I actually have like a whole a whole couple slides like dedicated to that aspect. But the TLDR here is that it's just really difficult to add agents to a game that kind of assumes a lot about how the states of the agents are stored, how the NPCs are connecting, things like that. Even before we even get into the game, there's actually a part where you need to select your character, and even that was like kind of unclear about how to actually connect that. So overall, this game, they didn't really consider, how we might have agents connect in the first place. And because of that, we had to go and, rewrite some of the code and actually get that to work more seamlessly for us. And so our very first pass, I mean, this is the actual PR that we have for me adding some of the initial like state and action sort of integration to get bots working. And there's like a lot of changes we had to make to the game to get that working. And even in this case, it was not even like, perfect. There's a lot of issues still, and so we had like another follow-up PR that actually let them like select their character and made sure all the different like client like networking aspects got set up correctly. And so overall, there's probably like thousands of lines of changes that we need to make to actually support agents correctly. And so I hope this serves as like a real world example of where if you don't think ahead of this for these sort of things, it can definitely get pretty tricky in terms of adding things later on. You're going to have to go and change some of your infrastructure a little bit. So. In terms of like how the things that the game actually did have set up nicely for us for agents was the different interfaces for thinking about how we want to have an agent do an action or read the state from the game. And so one really nice thing that they had was this action request data class. And what this action request data object does is that it simply just holds information about the action that we want an agent to take in the game. And so, for instance, in this case, I want to use the attack action. So I pass in the ID for that action. I have some sort of target I want to attack. And then there's some other like parameters you might attach to that action. And so this interface actually made it really easy for us to simulate some actions for our agents, whether it be attacking something, using an ability, moving throughout the game. And so this is sort of like where I would start in your project maybe, and we'll talk a little more about this also in a future slide about like thinking about action states. But definitely think about like the interface that you want to provide for your agents to call into, doing different things within your game. If you can have like a really nice kind of abstracted interface where it's simply, hey, I want this bot to do this action. Here's all the parameters. That makes things a lot easier, especially for things like now this play action can take into account like the animation system and whatnot, and also be used for an actual human player as well if they're playing the game. So yeah, definitely think a lot about the interfaces that you want to sort of support in your game. So yeah, just a quick wrap up of principle number one. So overall, the core idea is to think about how your agent is going to integrate into your game pretty early. Use separation of concerns as much as possible to ensure that your code isn't like tightly coupled together. Like we saw, like the networking code and the state of like the agents in the games was pretty tightly coupled, meaning that I needed to have like the agent be a networked sort of object if I wanted to get it to work properly. So it would have been really nice if that was like just kind of separated out initially. Use different interfaces to help encapsulate your code. Try to think about how you want to abstract away your state and your actions to make it easy to call into. And then also really think about like I'd say the layers of where the agents will live. And so what I mean by that is like how low level do you want your code your agents to be calling into inside your code? Like for instance, should I be using the nav mesh system directly? Should I be telling it to press these different key inputs, things like that? And that'll actually be also I think the third principle we'll go over in terms of like thinking about those different abstractions. But all those things are important to think about early on in your agent design.
Can I ask a question? I'm
Yeah,
curious.
sure.
Um, this looks really clean, but not but. And I wonder if your customers ever wanted to like exercise the input stack. Like, do you ever ended up implementing things that output, input signals like visual or I guess probably not visible? Like, is that an ask that comes up? And
Yeah,
for
yeah.
folks
Mm.
to just contextualize this question, what we just saw, basically creating actions, are not necessarily following the same path that the raw inputs from a controller, a mouse, and keyboard goes through. Which means if there's any bugs in that layer, the approach that we talked about is going to exercise, if my understanding is correct.
Mm. Yep, yeah, that's correct. And actually, I do have like some slides that go like very deep into that subject as well. Yeah, so we actually like a wide variety of folks in terms of like what they're looking for their agent integration. Sometimes they just want to simulate like direct key presses into the game. Sometimes you want to actually call into different functions within the game itself. And so it really does vary from like game to game and what the use case might be. So for instance, like with QA testing agents, you probably want to simulate the player like or the human player as closely as possible. So you might want to use key presses there so you can capture those bugs. Like if there's a bug, like when I click a button in the UI, I want to be able to see that, right? But then of course for agents that might be like an NPC, maybe that's a little bit less concerning, and maybe you could just use like the functions directly within the game. And so yeah, it really we've seen it all for across all the different studios we've been working with so far. All right, so principle number two is start simple. So I guess this might sound like it might go a little bit against everything you've been learning in this course, but this is sort of like I think a good sort of lead up into the things you'd be learning or trying out in this course. So I mean, there's so many cool approaches out there now. You have a lot of deep learning, deep reinforcement learning approaches, things like the Dota 2 OpenAI 5 bot. You have more recent things with LLMs like the Voyager system for Minecraft. And then even more recently, just a few months ago, you have things like SEMA from Google, which has been working on like a sort of a generalist AI sort of approach for games. And so there's all these like cool techniques and approaches out there that you'll probably want to try out. But I definitely urge folks to at least start simple and like really think deeply about what you actually want your agent to do and sort of like what are the capabilities that it needs to actually do that. And so I'll give like a real example from a real use case that we had once, which was a match three game. You can imagine a very simple game like a Candy Crush, where you have all these different pieces. You want to match them into groups of three, and then I'm sure you all know how how a match three game works. But this use case we were looking at is that they had a match three game that had hundreds of levels that they made by hand, and what they wanted to figure out was if any of the levels were too difficult to play on its own. So maybe like with the configuration of that level, maybe a player would get stuck 90% of the time. Maybe there wouldn't be any matches left. And so the goal was, can we actually program an agent to go and play these games, and then figure out, what percentage of the time did it get stuck? Did it get stuck, 50% of the time, and maybe that's a good level to have, or maybe it was never stuck, and that's like an easier level. Overall goal is to figure out like how difficult a given configuration is for the match three game. And so you may be tempted, especially with some of the techniques you learn in this course, maybe we could create a really simple reward function for this game. Maybe it's like simply, did I actually clear the board? And that's my reward function. And I can actually train like an RL-based agent to kind of go play itself and, get like some decent agent out of it, right? Maybe I just want to use an LLM. Like this would probably be a very, very simple prototype where you just kind of give it the state of the board and say, hey, what two pieces should I swap? Maybe you want to use some sort of goal planning approach. Or maybe you want to use imitation learning where you're actually playing the game yourself and teaching a model how to play correctly. And so these are all really good ideas, but there's actually like much simpler approaches you can use here for a match three game. I mean, a very simple algorithm, if you think about it, is simply just get all the possible swaps that are like, decent or available on the board, pick one at random, and then just make that swap, right? That's sort of like a very, very simple algorithm that you can start with just to see, how that performs and does that actually, sort of solve the use case. And so usually what I've always told studios is that you want to start as simple as possible and then evaluate and iterate where the downfalls of that approach is, and then think about how you might be able to improve either that approach or try a new approach. And you'd be surprised by how often this happens within game studios where they want to try out like very, very new approaches and just see how it works, where they're kind of just like ignoring like the really simple approaches just to start off with. I also remember this like at my previous job in space as well. Like, we'd have customers who'd want to use the newest and coolest NLP approaches to extract something from a document. And then, it turns out you could actually just use a very, very simple algorithm to get it out. Same thing for game agents. Sometimes a game agent doesn't, need to be some reinforcement learner model. Sometimes it could just be a very simple algorithm. And so our process when working with a lot of studios for actually designing agents is usually a very iterative process. So we'll first think of the use case. What is it exactly that you want the agent to do? Do you want the agent to, be able to be a human player? Do you want to just like easily interact with the player and not really have many complex actions? Do you need to go find bugs in your game? These are the sort of things you want to ask initially. And then I'd encourage you to sort of think of the most simplest algorithm to start, even if you think it's like not going to completely solve the use case. Just having some starting point is a really good place to, begin exploring like what sort of extensions you need to make to your agent. And also, this step really is good for helping you force yourselves to think about the behavior and making sure that your goal is actually like well structured in the first place. There's been a lot of cases where you might have an idea for an agent and you go start thinking about the algorithm and you realize that you actually like didn't define your goals like well in the first place. Um, and so, for instance, you might say like, of course, like, oh, I want this bot to go beat the player like 50% of the time. And then when you go start to think about that algorithm, you realize that there might be other sort of like goals you might want to think about, like whether, maybe if it's like let's say a game like League of Legends, does that mean that the bot is really good at like kiting abilities? Does it mean that it's really good at macro play, micro play? Those are sort of things you might want to think about as you're thinking about the goals of your agent. Then, of course, come up with a simple prototype, try out the approach, and evaluate where it falls short, and then just kind of iteratively go back and just keep improving that approach and seeing like where it falls short and try to address those areas. And then, really, I'd say like only once you exhaust the possibilities of that approach, that's when you probably want to try a new technique. Another example where it's important to think about, relating your goals to the actual agent you're building. I mean, the OpenAI 5, I'm sure some of you may have seen it before. It's the bot they made for Dota 2. These are sort of the results they had when playing against real humans. So overall, they had a 99% win rate. And so they're very, very difficult to beat. And so obviously, this is like a really great research agent. This is like a big, sort of a event in just the history of AI in games and getting agents to work in a really complicated game like Dota 2. But obviously, like you would not want to add this agent as like a multiplayer bot in the game, right? It's just going to be every single player. No one's going to want to play against that. And so there's just like where it's really important to think about, what is your actual use case? Think about what sort of approaches you want to take to actually reach that goal. Sometimes, training the best agent or using the newer approaches isn't always the best approach depending on the use case you're looking at. But so yeah, so just wrapping this up, I guess the key point I wanted to make here was, clearly define what your goal is with these agents. maybe it might be we want this agent to help the player learn how to play. Maybe it should be that this NPC should barely lose to the most beginners, but beat some of them. This agent should explore the level and find bugs of these types. It just really helps to clearly define what your goal is, and the more precise you can make it, the better. And so I definitely recommend that in your project. So like really write down like, this is what I want this agent to do, and here's the capabilities it should have, and here's some initial sort of approaches that actually might help us like get there. Yeah. All right, so principle number 3, thinking about states and actions. This gets deeper into some of the things we're talking about earlier or discussing earlier about, how do you think about the abstractions of your states and actions. Throughout the course, you probably saw many different types of state and action spaces. So for instance, one might just be screenshots. I know this is a pretty common one with some of these reinforcement learning approaches where you just get a screenshot and you want to use some sort of computer vision approaches or some like convolutional net to just like process all the pixels and eventually feed that into a model that you can train against. So that's like one example of like a state space that you might be looking at. Another one that's also very common, and especially in some of the ML agent frameworks and some of the game engines like Unity, is ray tracing, where you have your character, and what it does is you just send a ray out from the character in different directions and see what it hits, and then you use this as the state for your agent. And so this agent can see, oh, to my right or to my left, there's this box, and it's this far away. So that's like another example of like a state space you might be looking at. Another one, which is one that we actually use quite a bit at Regression Games, is just looking at the raw game state in general. And so this might be, actually scraping the hierarchy of the game and looking at all the different entities in the game, including like their positions, their rotation, all the different properties they might have. That's something that we've actually spent a lot of time building out as like a tool to automatically extract like a bunch of different fields and properties for game objects in Unity. And so we can, extract things like not only the name of the object and like position, but also like what's the health of a player, what's the cooldowns of abilities and things like that. And so those are a bunch of different sort of like game states that you might want to look at. And I'll actually show an example of this in one of our tools here. Let's put this up here. So Boss Room, like I mentioned, is this game for this sort of dungeon crawler game. And one of our tools that we have in Regression Games is that when you play the game, it can extract all the state from the game and kind of like show it to you in this nice UI. And so here we have like the screenshot, and then we have all these different entities that are inside the scene. These are things like all like the menu buttons, the character, anything that might be in the screenshot. And you can see here we have all these different properties. So we have, for instance, for a UI button, we have things like, is it interactable? What's like the image being used? What's the color? What's the material? All that sort of stuff. And basically what I want to get across here is that like there's a lot of different state that you can look at when you're designing agents. And so it's really important to think about what state is actually important to you and your use case, and what things do you want to use when training your agent or building out your behavior tree or whatever it may be. You're going to have a lot of information that you probably don't need, and then you might even have some information that isn't available, but you do need as well. And so what I find very helpful is to really start off by saying like, once we have a general idea of what kind of agent we want to make and the general algorithm we want to use, then what is the different properties we might want to load up and use in that agent. And so it's really helpful to kind of like look through what are your options like within your game and start thinking about that. And then in addition to the action to the states, you also have all the actions you need to think about. And so this is actually a pretty challenging problem. We've run into this for every game we've integrated with. There needs to be a decision made about where to integrate your actions and at what level of abstraction you're thinking about that. And so, for instance, one game that we were playing with once was a farming simulator. This year is Stardew Valley. We're working with a game that was kind of similar to that, but not exactly Stardew Valley. But you can imagine that maybe we want the agent to go and harvest some plant in the game, right? And so the very first step is to get to that plant. And so there's different sort of actions that this agent might take. Maybe you might think about it in terms of just like press the S key, which might move the character down like on the map. But then another layer above that might be just press the move down key. And so this is like one layer above in terms of abstracting, where we don't really know like what the key presses are, but we know like what the general action is to take to move downward. But even above that, maybe instead of just like indicating moving up, down, left, or right, maybe we just say, hey, move towards this position. This sort of like does a beeline right to that position. Maybe you want to use pathfinding. So maybe I can say pathfind towards X and Y. maybe I just want to say move towards the nearest plant, or even just like the overall action, which is just harvest a nearby plant. And so I guess what I'm getting at here is that there's a lot of different layers of abstraction for when you think about actions. And this is something that you'll want to define pretty early on. And depending on like the agent architecture you're going with, some of these are definitely easier than others. So for instance, if you're doing like a reinforcement learning algorithm, it's possible that like the direct like input or key presses might be a little bit better, just because of the way that the training works, and the way the data is collected. But if you're working with like a behavior tree, for instance, maybe something further down here that's more abstracted away might be better for that as well. Might help clean up some of the code. Um, I tell you right now, building a behavior tree where you have like a bunch of branches where it's like, oh, press the S key, press the W key, things like that. It gets pretty tricky pretty fast, and so it helps to kind of think about how abstracted you can make those different actions. Um, yeah. And yeah, I see a question here. Is it better to start compiling actions with high abstractions compared to low abstractions? And so, yeah, generally, I think it depends, like I mentioned, on the use case or the type of agent that you're building out. You really want to think about like how when I'm going to build this agent or I'm going to be training this agent, what level of abstraction is best for me. And usually it is probably best to like kind of think about the high level ones. Like if you can use a high level abstraction for some action, that definitely helps a lot. Um, but then of course there might be some requirements of your specific agent that might require to have a more low level abstraction for the action space you're thinking about. So yeah, but overall I'd recommend thinking at least about like the high level abstraction and seeing what you can kind of get away with at that high level, and then kind of moving down from there. Right. And so going back to an example here. So let me load this up. So this is an example of the uh, LM agent that I showed before, the agent that goes through and actually clicks the UI for uh, like clicking through the UI using like an LLM. And here our action space is simply like clicking a pixel like coordinate on the screen. And so that was like a choice that we made early on for this use case where really what the LLM is actually returning is like the ID of like some element that we want to click on the screen, but then we go and like convert that into a pixel coordinate based off that ID. So we can sort of look that up in the game and figure out where to click. And so that was just like a conscious like decision for us to say, hey, our action space is going to be selecting a component and then clicking on the pixel space of the screen. But then of course for the agents that are actually running around in the game, that's a little bit different. Actually, we actually use like direct function calling instead of direct like keyboard clicks or mouse clicks on the screen. And so one thing that's cool is that like for even just one game, different agents might have different action spaces or state spaces. And so definitely think about them kind of separately as well and think about what's just the easiest for you for your use case. So yeah, just want to share that example as well. All right.
And maybe just to contextualize this for the students a little bit more, would you mind switching to the previous slide?
Yep.
And yeah, to the slide where we were looking at the UI or the video, sorry.
Oh, yep.
Yeah. For example, like just to give an example, if the integration is done on the level of like selecting a component and activating the function there, that can probably click on the welcome player one, choose your class archer. If there's a button that was like occluded behind the settings, it would still be able to access it. But now when we're thinking about like clicking on a pixel level, then the input would most likely be blocked by the settings window. And that shows that different integrations can capture different bugs. This might even be a bug or not. But basically the level in which you integrate into the system actually changes the affordances of your whole tool that you're making. So something to think about, keep in mind.
Yep. And actually great that you brought that up because just recently, like in this past week, we ran into this exact issue with one of our action space like choices where we have one studio we're working with where we're trying to find some bugs in their UI where at some point when they're going through their game, like the UI just stops working. And we tried one approach where it was calling directly into like the on-click listeners for the buttons, and we couldn't find the bug, but the bug was still present when we were actually like clicking on the screen itself. And so that's an example of where like we actually need to look kind of like lower that abstraction a little bit and go a little bit deeper into like the actual like clicking on the screen sort of action space versus just calling into the code action space. And so yeah, so there's definitely real world implications of choosing one or the other, and it's important to sort of think about those trade-offs. But All right. So here's just another example of just like an action and state space that we worked with in the past. We have this tool in regression games called Agent Builder. Basically, it's like a behavior tree where you can also give it like a code prompt for basically writing the code for you, and it uses the context of the game to write that code. And so in this case, we're not really using like direct like key presses or like input into the game, but we're actually calling directly into like the mono behavior code. And so we can get like the state directly from the mono behaviors or call functions directly. And so that's just like another example where like for certain use cases, at least in the case of using these behavior trees for the agents we're building for this project, it was much simpler using it that way and much more direct, and was very helpful in like getting those agents built out. And so yeah, so overall, just kind of the main idea here, I guess, is that there's a lot of choices to make. Um, Here's, I guess, even another example. So for OpenAI, the OpenAI 5 bot, if you haven't checked out this page or this blog post, definitely would recommend it. But they also give some examples of the action and observation space for their game. And so, for instance, and they have like a bunch of like the abilities or actions they can take, like either attack or move to a location. And here they made like a conscious decisions like for attack, it's not going to be like clicking the player on the screen. They're actually just going to call that attack function for attacking that player. And then same thing for observations too. They made some interesting sort of decisions, like for instance, maybe it wasn't the observation part. I think for the action part too, like deciding like where to move to, for instance, they decided that they wouldn't just have like a continuous state space. They also would like discretize the space a little bit and choose like a grid point to move to. Um, and so yeah, overall, there's a lot of decisions to be made there about how they want to represent that action observation space. And then also for Mario here, I'm sure some of you may have seen this or before. There's like a pretty popular like PyTorch tutorial on training like an RL agent to play in a Mario game. So in this case, the state space is just the pixels of the screen. And then you'll see also that your input space is just like the key presses that you want to make, in the game as well. So once again, for this one, it was like a little bit more lower level, which tends to be like the case for a lot of these reinforcement learning based approaches. But anyways, it probably
Yeah.
was. Uh,
Sorry to smile and laugh there. I was like, oh, that's pretty impressive that they were able to play it that easily from pixels, and then the action spaces go right or go right and jump, which is, I think it's interesting to see, like, if you add a random agent that randomly presses those two buttons, I'm sure some of the times it will finish level one.
yeah.
Yeah, but it's cool to see.
Yeah, I think another one too for that is that like the choice of your action space, especially if you're training models, can also affect like your training time. So for instance, I'm pretty sure that like with the Mario agent, it takes like many hours to train. I think like 8 hours or so or more. And I've always wondered, I haven't actually like done experimentation with this, but I've always wondered if like we just exactly got like the information from the game itself instead of from a screenshot, would it be faster to train? My my thinking is probably yes, just because I might have an easier time learning just based on that information, but I'm not sure if that's
I am sure that is for sure. Yes, that's how I spent my first year of my PhD. And initially, I started with like basically the whole. So if I remember correctly, the NES controller has like 12 buttons.
Mm.
So when I first modeled it, I was basically, yeah, you can press any button in any combination, which meant the action space wasn't two, but rather like 2 to the power of 12. So 4,000 options. When you have 4,000 options, it does not train very fast versus two. And when like the difference is exponential.
Mm.
So yeah, and when you're extracting the state space, so much faster.
Yeah.
But
Yeah, that's a good
definitely,
point. Yeah, I think you could also
yeah,
get creative with this stuff too. Like I'm sure like with the gamepad one, right? Like you mentioned, like it might not be that maybe there's like some buttons that are close next to each other that you're never going to press at the same time, right? And so, things like that you can always think about when building out these things.
one thing that we did that helped was we basically filtered all the combinations that the human never pressed. So I played
Mm.
the game for a little bit and just like narrowed down the action space to the only things that human pressed, which was like, I don't know, 8 or 12, something like that. So that seemed like a grounded way of reducing the action space.
Yep. Yeah, that makes sense. Cool. So yeah, just kind of wrapping up this discussion here. So yeah, so when you're thinking about the state and action space of your game, you want to think about, especially for states, like where does the state live in my game? How do I actually go and extract it? Sometimes it's like really easy to get like, for instance, the health of a player, whereas maybe getting like the inventory might be kind of difficult. Like maybe there's some sort of abstractions or like special code you had to like try to understand to get that to work. So thinking about how you access the state is very important. Think about like how to filter down your states. So do you need like just a few simple properties from these game objects, or do you need to know a lot of different properties to actually get your agent to work? This would be pretty important, especially for the machine learning approaches where you might just like say, hey, I'm just going to put every single property here into like a vector and put that into my model, but it's possible that you actually don't really need all that information. And really just think it just like on a human level, like when you're playing the game, what information do you need to make like a good decision? And that might help you figure out like what does your agent need to actually have a good serve training approach. And then of course, yeah, for actions, think about that abstraction. Do you want to use the raw input or actually call helper functions directly? If your game is continuous, can it be discretized a little bit or at least simplified in a way that would make running an agent a little bit easier? And then also, are there any actions that are easily implemented by code? Is there any sort of like helper functions that would just drastically, reduce the amount of load that your agent needs to handle? That's always good to think about those as well. Um, but like I mentioned, regression games, like across all the different games, we've really tried all these different things from, directly extracting the state, doing some JSON output of all the state, even like just tagging certain things within the game, the ray tracing, screenshot capture, all these different things. And really what it comes down to is it depends. So you just have to think about like your use case and what you want your agent to do. And then that's how you want to design that action in state space. So yeah, principle number 4, we want to think about where the agent code will live. This is definitely a big point of pain, I'd say, working through some of these agent integrations. Um, it's actually not always clear like where your agent code will live or how it'll work. If you have like a single player game and it's like a very simple single player game, that's probably going to be the easiest situation where at least in Unity you might have like a mono behavior that just kind of implements the logic of the agent. But once you start kind of getting out of that realm, it gets a little bit trickier. You might have a multiplayer game where you need to consider like where the agent code is running if you have multiple servers or multiple players connecting. If you are using machine learning models, in most cases, you're probably going to have a model that's like small enough to run locally, but maybe your model might be too large, so you need to think about like where to host that model. And then, of course, sometimes you might be using external APIs. If you are using, things like LLMs or ChatGPT for, generating dialogue or making LLM-based decisions for an agent, there's some considerations there as well. And so I'll just start off very quickly with like the multiplayer aspects of this. I won't spend too much time on this because there's a lot you can always talk about the multiplayer, and I assume that most of the people in this class are not going to be doing a lot with multiplayer. So yeah, so I assume it may not be as relevant, but something that's important to think about as well. Um, and so there's at a very high level, there's a couple different multiplayer architectures that people think about when they make games. One is where you have a bunch of different clients that are playing the game, and then one acts as the main server that everyone connects to. Another one is where you have a dedicated server where all the clients connect to that one server. And then also you have this peer-to-peer approach where every client is kind of like connecting to the other ones, but there's no like central server that's like kind of coordinating everything. And so I just wanted to mention at a high level, like some of the concerns you might want to think about when building NPCs or agents for these games or for these different architectures. So for instance, let's say we have the client hosted architecture where we have one client who's kind of like hosting the server for everyone. Um, you have to make a decision for an NPC. Does that run on the host? What happens if this client disconnects and that NPC was running? You might have to like transfer the actual logic and like running of that NPC to another client who's now the new host. You might have an issue where maybe the person that's hosting the game is like has a pretty bad computer or maybe they're on like a mobile device and they can't actually like host a bunch of NPCs that are running around. And so that's where you might want to think about like how are these where is your agent actually running and what are the different constraints that it may be running in. Same thing for like the server-based one as well. If you have like a central server, this one has been really tricky, especially for that boss room sample or other multiplayer games where you have like agents connecting as players. Do you want to actually like simulate an agent connecting as a client, or do you just want to have that running in the server? That's like an important question to ask. And of course, if you have like let's say a big MMO, you have a bunch of NPCs running around, like where is that managed? Is that going to be managed on one server, multiple servers? That's something to think about as well. And then finally, peer-to-peer. This one's probably the trickiest one because let's say you have like some agent running around as part of the game, but it's not like associated with one person in the game. You're gonna need to think about like where like what machine those NPCs are run on. if that client, once again, if they disconnect, what happens to that NPC? Does it get transferred to another machine? So there's a lot of things to think about when getting into the networking architecture. So hopefully, yeah, it'll be great that probably most of you won't run into this right now, but in the future, hopefully as you use more AI agents in your career, hopefully, you might run into some concerns with this.
I actually
Um,
am
yep.
not very experienced in network architecture, and one question I would have is like, how does the games industry often go by? Or what I mean is like, which of these is the most common? I
Yeah, it's
actually don't know. Yeah,
yeah, I kind of seen like a mixture of approaches. I think like the peer-to-peer is probably not as common right now. I think what I see is like often like I think the dedicated server is definitely much more common these days, just like with how big like games are growing. I think this kind of makes the most sense. But we have had a few customers with the client host approach as well. And that definitely makes it a little bit trickier. But yeah, so I'd say like probably the dedicated server is definitely what people are moving towards. But you do see these other ones pop up once in a while, especially if you have like a very simple game. You can imagine like a very simple like mobile game that has like a match where you're playing with other people, like those might be like peer to peer, just might be a little bit easier for them to implement. And so it varies quite a bit across like game genre and platform.
that makes sense. Thank you.
And if you are curious to learn more about this stuff too, for anyone, there is a Unity page that has a bunch of information about like these high level architectures. Um, at the end of the slide deck, by the way, I'll have like a link to some of these resources as well as to the slide deck. So if you want to look up some of those, we can send those along. Right. So just a very quick example of this in Bostrom. So in Bostrom, it is a dedicated server approach where the server is basically like the same code as all the clients, except that it knows that it's the server owner and it's made kind of like available through this like .is owner property. And you see here like it basically tells you if like this entity in the game or this game object is owned by like that machine or that player. And so basically what like, we get to do in our code for Boss Room is that we can run the NPC code inside of these little like conditionals that say, hey, if I'm the owner of this machine, then actually run this NPC. But we do have to like add some code if we want to like have it be robust to different sort of connection issues happening. All right. Uh, I guess the key takeaway from this is overall, always try to just run your bots or agents on like the main host or server. Um, and the reason why I bring this up is that we've actually talked to quite a few studios where they're trying to or would like to like basically simulate a client connecting to the game as an agent. And so this is very common for like multiplayer games where they might have they want to like have agents that people can play against, so there's not many people online or things like that. And often their first approach is, hey, can we just take the game client and like have a player like connect like with that game client? Um, it turns out that's like very, very difficult because just like the resources to run an extra client somewhere as an agent is like pretty heavy. And often there's a lot of like code that is relevant to like client connections that makes it really hard to get an agent working. So for instance, I mean, even if you have any game that has like a cheat code or a cheat like sort of system, you can imagine like you can't just like simulate a client like in a virtual environment, just have it connect, right? Um, of course, if you're the owner of the game, you probably can like add some configurations to make that work, but it's going to be a lot of work to get that up and running. And so overall, we usually try to recommend to our studios that we're working with to try to implement the agents or bots like in the main server or the main client. Um, and only if you're like a very large studio, like, if you're making, Call of Duty, you probably have a bunch of machines running like consoles that are actually running the game and testing things. So in those cases, it makes sense if you have the resources, but in the most case, we're going to want to run these locally.
We had a similar experience where we were trying to integrate as a client, but the game didn't have a headless mode, which
Hmm.
meant basically headless mode is when a game runs without graphics. But this meant that basically for every single bot that we need, all the rendering and all the pieces that were visible and very expensive had to run. That did not work very well.
Exactly. Yep. Awesome. And then another thing to consider when thinking about where your agents are running is the performance constraints. Especially for like the machine learning agents, this is probably more of a concern. Obviously, you're making like a behavior tree or some other approach like that. You're probably not going to run into this issue as much. Um, but if you're working with like different reinforcement learning models or or LLMs, you'll have to think about like can the device that I'm targeting actually run these? And so if you're, targeting like the PC market or like the mobile game market, you might have different like sort of constraints for what size models you can run. For what I could tell, a lot of the RL models will probably be training are like usually not that large, and so I don't think those are like as concerning. But of course, with a lot of people using LLMs now, that can be a little bit trickier if you want to like host an LLM on your own device. There has been a lot of like cool work going on with this. So, for instance, like Gemini, I think just launched a couple weeks ago, like a new iteration of their Nano model, which is like a smaller model meant for devices. And so they actually got like a 1 GB size like LLM working on device, which could be useful for maybe running some LLM based agents that are doing dialogue or decision making using those. And so overall, you just want to think about like the constraints that your platform is going to introduce, and then use that to help you make decisions about how you're going to be training or building your models or your agents.
The fun thing about reinforcement learning models is that oftentimes they are actually two models. One is a value network, the other one's a policy network. The details don't necessarily matter too much, but the value network is tasked with understanding how good things are, and the policy network is tasked with just being as good as it could be, given the output of the value network. And in inference time, you just need the policy network. And the neat reality of things is the agent performance scales very drastically with the value network size. So you really need a lot of like information capability to understand how good a position is. But you don't really need that big of a policy network. All that is to say, you can train a pretty big network, extract a little bit that matters at inference time, and put that in. There's a funny paper called "Honey, I Shrank the Actor." It just like looks into it. So it's reinforcement learning gets a pass in this axis, which it needs all the help it can get to be relevant. So it's nice.
Awesome. And yeah, and also a lot of the game engines are making it easier to add models now as well. I think like even if we talked about this like a year ago or 2 years ago, like you'd be kind of like on your own trying to load up some of these models, but a lot of the game engines are now just supporting it directly out of the box. So for instance, Unity has Unity Centis, which allows you to like load up machine learning models pretty easily into the platform. So I wouldn't be surprised if some of you might even be looking at that for some of the projects maybe. Um, and then also, I think Godot, back when I thought this course was being taught in Godot, there is like some Godot RL agent like frameworks as well out there that lets you kind of easily load up and train agents in the game as well. So yeah, there's a lot of tools out there that make it a little bit easier to load up these models and get them onto the device. So um, and overall, I'll just wrap up this slide or this section with we really learned the hard way at regression games about like where to run agents. We really tried pretty much every single approach. So back when we were doing the Minecraft tournament, how that worked is that the agents were actually like running in a separate server, but on the same machine as the Minecraft server. And so the actual like networking was like pretty simple. There wasn't really any latency there. But we basically communicated over like TCP or HTTP calls for basically setting actions and state from the game and to the agents and back and forth. When we started doing things with Unity, we kind of did the same thing where, could we have a server actually running the agents? We send HTTP requests with the basically setting along the state and then getting back the actions. And we thought that worked kind of okay for locally, but as soon as you have that agent server running on a different machine, because now we have Unity running like within your own laptop or desktop, and then we have like the agents running in the cloud. Like that became pretty tricky because the latency introduced is just like not going to give you good real time agents. So we tried things with that. Even within the game itself, we got a little complicated or tricky where like we were trying to run agents like outside of the Unity process, so we can run agents in different languages. So for instance, maybe you want to write an agent in like Python or JavaScript. Can you then run that like in a separate process and then call into that from Unity? And so we really tried all these approaches. In the end, turns out sort of the best approach was just running it directly in Unity as like model behaviors or C# scripts. But I've always had a hope or goal in the future of like, can we support other languages and other processes for some of these agents? Might make it a little bit easier for folks to build on top of. But yeah. And so the last part of this section is also thinking about like external APIs, especially if you're working with things like ChatGPT or some of those approaches. Um, LLMs can definitely add like seconds of processing time, and so you want to make sure that your specific use case or agent like is fine with those sort of like latency constraints. So for instance, like if you have turn-based game or like a like dialogue for an agent, maybe that's fine for an LLM, but maybe for like some real-time action decision making, it's not as good. Um, and then of course, if your model is too large, you might need to like host it elsewhere. I don't think you'll probably run into this too often, but there are some things you can think about as well to kind of still get your model on device. Like, can you just train a smaller model and see if it works? Can you quantize the model? That's been like a popular approach, just making these models smaller by reducing the size of the weights inside the model. Um, and then also going back to one of our previous principles, like, are you going a little bit too complicated with a huge model for your approach? Maybe, a simpler approach would work better. Um, and so overall, you're just going to need to consider all the different trade-offs when thinking about these things. Um, I guess a quick side note on like one tool I use for like the LLM agents. I've been doing a lot of experimentation with those lately. One tool I found really useful is a tool called Langsmith, which basically I use LangChain as like my main like framework for doing a lot of experimentation. And they have this tool where I can actually go and see like all the different latencies and like cost and things like that of the agents that I'm working with. And so I definitely recommend checking them out. Looks like it just disappeared, but yeah, you get to see like all the different like latencies for how long it takes for your model to run, how long to respond, things like that. So things like that can be useful as well. So yeah, so overall, try to put as much logic into your game as possible. I usually find that way is the best way to build out these agents. And then also avoid client simulation when possible. It just makes things very, very tricky. And then if you are using external services or large models, just consider those trade-offs of latency and the devices you're working with. So, all right, moving on to like the last principle here before we have some just simple tips and tricks to wrap it up. I'd say that one thing that people forget to do is really set up a way to evaluate your agents. It's very easy to get excited and say, "Hey, I have this cool idea for an agent and go build it out, try it out in my game, and that's it." But actually finding a way to like reliably evaluate it over time and make improvements is very useful. And so first step, of course, is you want to think about your evaluation metrics in the context of your agent goals. So, for instance, if you're making a multiplayer agent that is supposed to, barely beat players, maybe your evaluation metric should be, across like X many games, it should only win this many matches, right? I mean, that's like a metric to calculate. Um, and then also, one thing that we find very useful is to like build a simple scene or like environment to test your agent in. This is like not an agent, but I thought this was like pretty relevant to this as well. I saw this post a few months ago where this person's building like a parkour game, and one, it just looks awesome, but two, they have this like really nice environment that they have for testing. And you'll see like they have all these different sort of like edge cases in here as well. So they have like different like walls or things you need to drop down into, or these like little loops to jump through and things like that. And so, even though this isn't for an agent, you can imagine that if you were to build an agent for a game like this, having an environment like this to test in would be like very, very useful. Um, and so I definitely recommend start investing at least some time into like building a simple starter scene for yourself to play around in. And then of course, last part of it is just like to collect real data and iterate, like actually see like how your agent is doing based on these evaluation metrics, and then do some like A/B testing as well of different ideas and see how they might work. So some other examples of where this is pretty common is like if you work with the ML agents framework in Unity, or like an OpenAI Gymnasium, they'll have like a bunch of these different environments just to test out agents in. And they're usually pretty simple and kind of like just let you focus on the agent. It's especially if you have like a pretty complicated game, you don't want to have like to get through like all a bunch of different dialogue and like story and things like that to get to your actual agent behavior. You want to kind of just like go and test it right away. Definitely saves a lot of time. A very simple example of this, as well as like in a racing game that I was playing around with at one point. Um, I was trying to build out an agent, just like trying out different approaches. And so I started building the agent, and then I was like, wait, how do I even tell if this agent is good or not? And so I started collecting a bunch of metrics like how often was it turning, how often was it hitting the wall, how long did it take to complete a lap. And so I was like data I was collecting so I can evaluate. In this case, I was trying out like a behavior tree approach versus just a simple rule-based approach versus like eventually like an ML agent approach as well. And so that helped me a lot in terms of figuring out like how good my agent was doing, and also if a change to my agent actually helped like make it better. And so you can always start pretty simple with this as well. You don't have to like make a huge evaluation framework, just at least start tracking some things to see how your agent is doing. So yeah, so just wrapping up that principle, yeah, make sure to evaluate often and really connect it back to the goals of your agent. If the goal of your agent is to be a fun, agent to play against in a multiplayer game, doesn't it make sense to have a metric be, win as many games as possible? You want to make sure to kind of relate them to each other. And then, yeah, just make sure you have the environments to test things out in. All right, I guess, and then to wrap up this talk, I wanted to kind of just go through a few tips and tricks really quickly. That weren't really like big principles, but like things that I found useful. Um, One, don't be afraid to expose extra state and actions to your agents. So a very good example of this is like, let's say in a game, maybe a player has an inventory, and maybe if you're an agent playing against that person, you wouldn't really get to see the inventory, but maybe having that inventory information actually would help your agent like make some decisions that would improve the player experience. Then you might want to expose that information, even though a human wouldn't have access to that. Um, Same thing for like ability cooldowns. Maybe that would be like an example, like in a lot of MOBAs, that you can't see your opponent's like cooldowns for abilities, but maybe giving an NPC the ability to see that would help them a little bit. Also things like teleporting or just item spawning inside the inventory of an agent, like things like that are pretty useful. So don't get stuck in the trap of like, oh, a human player can't do that, so I can't let the agent do that. Like you can always think outside the box a little bit. This is a big one, letting agents have like more power than human player, and this is like related to a use case we had for a 2D platformer. We had this use case where we had a platformer where you'd have an agent like walking through the platformer to validate that a level could be completed, and we found that like when implementing this agent, it was really really hard to get the agent to like jump onto the platforms correctly. It would often like just barely miss the platform, even though it should technically be able to reach it. And so we're spending so much time trying to figure out like why this agent wasn't working, and then we're like, you know, why not just let this agent have slightly better jumping power than a human, right? just barely like maybe like 10% more jumping power. And so even though it was like a very simple change, it helped save a lot of time and kind of like got the job done for at least that use case. And so giving them these like little extra like performance improvements that a human player wouldn't have can help a lot too, with kind of depending on your use case there. Um, Implement debug tools. Also very important. I usually try to start off the projects by doing this kind of right away. Whether these be like very simple console like log statements, or in the case of that racing game I just showed, you'll notice that like the agent has this floating text above it that says like the distance to the next waypoint, the angle to the waypoint, and then how many waypoints are left. Because in this case, the agent is a waypoint following agent. And so having things like that definitely helps. You don't realize how helpful it is. So you have it implemented. You're like, wait, this has saved like so much time trying to figure out why this agent isn't working or isn't doing the thing I wanted to. Um, Similar to that, we also like built out a tool like in our framework for doing like replays of runs by agents. That was like another debug tool we built out that was very useful, so we can actually like see like how an agent what it did over time. Um, we even have one other kind of not really a debug tool, but a helper utility like within our Unity games, which is also very useful. We have in Boss Room, and I'll actually just show this live here. So when I get into a game, like one very tricky thing that you might find is that you might like write an agent that you need to just like restart your game to like get to load up. Um, and also you might need to like keep like adding agents like objects to your hierarchy to like get an agent into the game. But what we built out was this overlay that lets us spawn agents into the game while it's running. And so here I can actually just like choose a mono behavior that I want to run, and I click start bot, and it'll just like start that bot for me. And so I can start a bunch of them and just like let them run through and can kind of evaluate them. And so a tool like that helped us a lot in terms of like just iterating on agents really quickly. It was nice kind of having that control over them as the game is running. All right, and then trick number four, thinking outside the box. This is something I actually learned at the game developer conference this past year. There's a lot of like really interesting talks about like AI agents and how studios implemented them, and so I definitely recommend checking out like some of those resources. But one that really stuck in my head was Call of Duty. The zombie mode has this monster called the Orda, which is like a really big zombie. And they had this really interesting talk where they found that when they went to implement this agent, just the fact that it was a large NPC made it really, really difficult to implement it, because a lot of their things they had previously for agents like broke down. So, for instance, their pathfinding system just assumed that like all agents can fit through doors, but this can't fit through a door because it's too tall. And so Things like that were really a big issue. The animations were a big issue where smaller characters, when they turn, you can't really like notice like their feet sliding because they're so small. But for a large agent like this, you actually notice like pretty considerably that like they're sliding on the ground. And so they had to come up with a bunch of like interesting like AI like animation approaches and like different like pathfinding approaches for getting this NPC to work. And so I don't know, it's a very cool talk just like about like how they thought outside the box a little bit about like, how to re-implement some of these systems to work for some unique NPC that they wanted to implement. So another trick which you could find useful, this might have some limited application, is that you might be able to simulate your game. And so, as Batu was mentioning, with like a headless mode in games, that makes it a lot easier to run a game very quickly without graphics. But sometimes you might not be able to get that headless mode running. But if your game is very simple, like maybe it's like a puzzle game, you might be able to do some sort of just like numeric simulation of the game. It makes it a lot faster to execute, but the problem is that it's not going to be the actual game. And so, depending on how your game is implemented, it might not be an exact like sort of replica. And so, a lot of folks I see try this out, and like depending on the game, it might work, but often it also is like tricky to get working correctly. So, it's something to think about depending on your game, but could be useful. And then finally, definitely use built-in tools to your advantage. One interesting thing for all of our agents that we built out in Unity so far, for instance, is that like we almost always use the built-in like nav mesh system for navigation. We never really have like agents try to like learn their own navigation system or like kind of build it out ourselves. Like sometimes they're just tools that work really well and you want to try to use them to your advantage. Similar, and Godot also has like a similar one where you can kind of like lay out sort of a navigatable space, then you can have they have like a similar nav mesh system. And so yeah, just wanted to mention like definitely see what's available like in your game engine and see what you can provide. Um, and definitely use them if you can. Yeah, so I think that was most of what I wanted to chat about. I guess just wrapping things up. If you click on these links in the other resources slide, once I send these out, you'll see one, like I just mentioned, if you type in GDC agents on YouTube, there's a lot of really great talks about implementing AI agents at larger game studios. There's also a few Discords I really like. One is there's an AI in games Discord where a lot of people are just talking about just implementing agents in games or other AI approaches in games. Of course, it's also regression games Discord. Love to have people there and trying to chat about just like different AI approaches in games. And yeah, just to recap, we talked about thinking early about what your agent goals are and how you want to actually approach the problem. Start off with a simple agent and iterate from there, and then try more complex approaches as you move along and find sort of like downsides of your previous approaches. Make sure to like really think deeply about your state and action space. There are a lot of options there, and so you could consider multiple ones and see what works best. Decide where your agent code will run. I think for all you'll just kind of run right in the game, but it could be a thing to think about depending on your use case. And then finally, make sure to actually figure out how to evaluate your agents effectively over time. And this is shared at the very beginning as well, but we have a site that you can check out if you want to learn more about us. Regression.gg is the website. And we also have a GitHub where we have some open source packages as well that we're always trying to improve. And I think we'll be adding some more over time as well. So definitely check that out. And yeah, that's all I had. And here are the links to our Twitter as well as my Twitter. I try to post a lot about AI agent stuff going on. So yeah, really appreciate everyone listening.